Hello, my name is Jumpei Saito from Keio University. Today, I will present our work titled A Tendon-Driven Bead-Based Spine for Shape Adaptive Mobile Robot. First, let me show you how the robot moves. The robot can move forward and backward, turn by bending its body, and lift parts of its body to interact with the step. As you can see, the body does not remain straight during locomotion. Its shape changes for each behavior. The turning and lifting motion are produced by changing the shape of the robot's body. Wheels provide efficient locomotion on flat ground. However, most wheeled robots have fixed body and fixed wheel position, so they have limited ability to adjust their contact with obstacles. In our robot, three rigid modules are connected by two flexible bead-based spines. By bending or lifting the spine, the robot changes the relative position of its module and wheel. In this way, body shape adaptation becomes part of locomotion. The key component is the tendon-driven bead-based spine. Small beads are woven together to form a flexible structure. Two tendons are placed on opposite sides of the spine. Pulling one tendon and releasing the other bends the spine towards the pulled side. With tendon tension, the spine can actively form a commanded shape. When the tendons are released, it can deform passively in response to external contact. The important point is that the same physical structure supports both roles. We integrated two bead-based spine between three rigid modules. The robot has 5 motors. 2 motors drive the front and rear wheel, while 3 tandem motors control body bending and lifting at the front and rear. Fully rotation passive wheels support each module. A max send motor command through a U2D2 interface. The wheel motor receives velocity commands, while the tandem motor uses current-based position control to limit excessive pulling. The demonstrated motion uses predefined open loop sequence. This slide shows passive deformation during interaction with a step. On the left, the lifting tendons are pulled to actively raise the front module. After the wheel places the front module on the step, the lifting tendons are released, as shown on the right. The bead-based spine then deforms passively in response to contact while the robot moves forward. The same structure therefore changes from an actively controlled lifting element to a flexible body that responds to contact. This sequence shows the beginning of step ascent and the passive deformation during contact. In summary, the bead-based spine has two roles. Tendon actuation actively bend or lift the body. Releasing the tendon allows passive deformation in response to contact. Using those modes, we demonstrated curvature-assisted turning, lifting, and interaction with a 30 mm step. Combining the two roles may extend the locomotion capability of wheeled robot. Next, we will quantify performance and repeatability and compare the robot with other locomotion systems. We will also integrate power and control on board and expand its locomotion behavior. In this longer term, The mechanism itself may handle part of the interaction with the environment. This is our direction toward more reliable and versatile shape adaptive locomotion. Thank you.